And then even in the presidential debates, Kamala Harris referenced quantum computing. So what are we talking about, Sam? Like, can you give the audience a sense of like, what is this fancy thing called quantum computing?
Sure, I can try. So every computer that exists today or has existed, from your phone to the world's biggest supercomputers, are all based on the laws of electricity and magnetism. And so that's sort of driven the development of computers for decades and decades and decades. But it turns out that at very small length scales and energies, there are different laws of physics, quantum mechanics, and matter can do some surprising things. So it can be in what's called a superposition, which is multiple states at the same time. It's not just that there's a 50% chance of a coin being heads and tails. It's actually both until you measure it. It can entangle with other matter such that its state is shared and can't be separated. And you can learn information about the state of one part of matter by measuring the rest of it. And it can interfere. So if you're familiar with the way that waves can constructively or destructively interfere, particles can do that too. And it turns out that if you can harness that in certain ways, you can create computers based on quantum mechanics that have the potential to solve some problems that computers based on electricity and magnetism cannot. And we're not sure yet exactly how big the set of problems that is yet. But already we think it's some pretty important problems related to simulating chemistry, simulating biology and material science, with applications in things like drug discovery and more efficient energy. So we're all working on trying to make that a reality.
Great. All right. So Matt, can you tell us how you're working in quantum computing these days in your company?
Sure. And first of all, thanks a lot to DLA Piper for organizing this. Really happy to be here. I would just pick up on what Sam just said. So what Sam is describing is a new kind of compute technology that has the ability to solve problems much more quickly. So a much more powerful processor, in the same way that if you had a CPU back in the day doing all of these different workloads, along came NVIDIA GPUs, and they boosted the performance for certain types of math problems. So the one that we care about, our company spent a lot of time trying to take a view on what would be the first type of problem that could be accelerated with quantum computing. And just to riff on what Sam said, we believe that will be in the field of simulating the electronic structure of molecules. So in other words, simulating physical systems. And in particular, that's interesting from a commercial point of view, because designing new molecules is fundamentally what you need to do to come up with a new drug, a new material, a new catalyst, a new chemical. So the software market for chemistry simulation software right now is kind of a static, somewhat large, but kind of a static field. And so we think that the first use case will be evaluating properties of molecules and doing that in not just silicon, but doing it on quantum processors. So what our company, in fact, did to try to exploit that opportunity was to first build a software package that today runs on NVIDIA hardware, just giving a little bit of accolade to Sam once again. But it's architected our software so that as soon as one of the 50 or 60 quantum computing hardware vendors out there comes up with a chip that can do something more efficiently than a GPU, we'll just slot that into the GPU workflow. So from a user perspective, all they're going to see is that when you introduce a QPU, you'll get a power boost. You'll be able to simulate larger molecules, or you'll be able to simulate molecules more quickly. So to come back, that's a long-winded way of saying we think the first real practical use case for enterprises is going to be in the field of molecular design.
Cool. And then Grace, what's HP doing in quantum?
Yeah, so I'll just kind of also briefly echo off of what Matt was saying. We also think that the most promising applications are in simulating quantum physics. and quantum chemistry. And in fact, that was kind of the original conception of a quantum computer, was from Richard Feynman in the 80s. Like, if you could build a system that's based on the same kind of fundamental physical building blocks, then you can actually simulate it more efficiently, right? And so basically, simulations of quantum systems, if you do them on a classical processor, are inefficient. So the position of HPE as a world leader in supercomputing, customers were sort of asking us, what's next, right? And I work at labs, and our kind of goal is to look 5-10 years out in the future. And so our view is that, supercomputing is growing increasingly heterogeneous, right? You have CPUs, you have GPUs, TPUs, various AI type of accelerators, and you can kind of view a quantum computer or a QPU as just another specialized accelerator. So our goal is to think about how you would integrate QPUs into HPC infrastructures, and really the idea there is, how do you scale up, right? Because as Matt was saying, all of these hardware companies that exist, nobody has a processor yet that shows quantum advantage for a problem that we care about, like drug discovery. So we're really thinking, how do you integrate, how do you scale up?
Got it, great. And then Sam, what about NVIDIA? What's NVIDIA doing in quantum?
Quite a lot these days, actually. So we see quantum computing build on what Matt and Grace said, as a really important part of the future of accelerated computing. And so NVIDIA has, I think, core to what we do for a long time has been working to help new accelerated computing technologies and new computing technologies that can solve important problems develop, try to enable our partners, leading researchers and groups in the world to be successful, figure out what problems we can help them solve, and figure out how our technology can fit in. So that takes a few different flavors. It comes from building, or includes building powerful simulation tools on GPUs, tools to use AI to help with quantum computing, either research or in the future in production, and tools for integrating quantum computers with CPUs and GPUs, with supercomputers, so that supercomputers can benefit from quantum computers and vice versa.
Got it, great. So we talked a little bit about the benefits of quantum computers in drug discovery, but there's other benefits that quantum computers can have. Grace, do you want to talk a little bit about the other aspects that you're looking at and where you think quantum computing is going to have the biggest impact?
Right, sure. So I think that simulating quantum physics is the most promising, right? And that's because the problem is just naturally fits in with how a quantum computer works. And you really need to think about what a good quantum algorithm is. And like Sam was saying, a quantum computer works in a fundamentally different way from a classical computer. So we don't have kind of the analog of like memory in a quantum computer yet. So the best quantum algorithm is one where you have a small amount of classical data that goes in. Then the quantum computer does something fancy in there that you don't really need to see, right? And then
magic, right?
Magic, right? Quantum, entanglement, all the fun stuff. And then you take a measurement and you get out a small amount of classical information. And so simulating quantum physics is that. Things like optimization and machine learning, they're algorithms that people are developing, and there's really interesting work there, but they have to overcome a lot of challenges because, they need to load the data in somehow. Mm-hmm. So there's potential certainly in areas of optimization and AI, but challenges that they need to overcome. So the most promising is simulating quantum physics because it matches those criteria. And then there's, of course, integer factorization for breaking RSA encryption. So that was developed by Peter Shor in the 90s. And of course, it's probably a reason why we're here today through the lens of kind of national security topics.
Yeah, so I think that was brought up in the first talk with General Mattis. So Matt, do you want to explain a little bit about what this issue is with RSA and cryptography, and why some people are saying quantum computers will bring doomsday to how our secured transactions and security of, like, say, banking will work?
Sure, I can build off on what Grace said. It does. So back, I think in 1992 or 95, a Bell Labs researcher, who's now an MIT professor named Peter Shor, came up with a way to do something practical with the quantum process. Keep in mind, back then there was no hardware. But he came up with a way to take a large public key, a large string of digits, and derive from that, calculate the prime numbers that, when multiplied together, would produce that string of digits. And that, by the way, doing that is typically a computationally extremely hard thing to do, which is why it was the basis for this particular type of encryption protocol called RSA. So governments around the world at that point started to pay more attention to this. They didn't panic because there wasn't a quantum computer in the mid-90s to run on. But there's been a lot of effort to build quantum machines so that this particular extant algorithm could be exploited. In the meantime, of course, everybody who cares about protecting data has looked at other types of encryption protocols which are resistant to that particular algorithmic approach to break that code. So I think it's kind of it's going to continue to be a cat and mouse game where quantum processors are going to be used to help develop new decryption and encryption protocols, and that kind of cloak and dagger thing is as old as kind of civilization, I guess. But short answer to your question, that's it.
Okay, great. And then Sam, if quantum computers can break RSA, do quantum computers also provide a solution for a new type of security mechanism?
It's a good question. There are proposals for that. The most, I think, promising and near-term likely to be adopted protocols for replacing RSA encryption are not from quantum computers, but are from a different set of mathematical problems, which, as far as we know, are really hard still for both a very large quantum computer and a very large classical computer. So it turns out that quantum computers can be exponentially more efficient at the factoring problem. There's an effort worldwide to standardize these new algorithms, which are called post-quantum algorithms, which are mostly based on a problem around giving you a very large set of data points and asking you for the vectors which come closest to them. And so it's one of those problems where if you already have the vectors, it's easy to check, but if you have the data points, it's very, very hard for either a quantum computer or a classical computer to figure that out, as far as we know. So these algorithms are actually got standardized this year.
Last month even, right?
Yeah. Just recently.
Yeah.
And companies are actually already starting to migrate. The main reason being concern about a hack now, decrypt later attack. So even if a powerful enough quantum computer is not close to ready, you could imagine stealing encrypted data now and decrypting it when it is ready. So if you have data that you want to protect for many years, companies are thinking that they should start migrating that as soon as possible.
So you said, you're alluding to like when these quantum computers are available. So what's available now? Like what are the quantum technologies that are available for use now? Or maybe better yet, like how many qubits? Because qubits, so each quantum computers, they don't have bits, they have qubits, right? So like how many qubits are in a current existing quantum computer? Matt, do you want to take that?
Sure. I guess, so first of all, there's, again, something like 50 or 60 hardware vendors that are producing quantum computers. And if you peered into the designs of those 50 or 60 quantum computers, there are 5 or 6 different technology approaches, which is another way of saying there are 5 or 6 different types of qubits. A qubit is a physical device. It's like a transistor, call it a quantum transistor. It could be a photon, an atom, an ion, loops of superconducting wire. So there's all sorts of different designs. If you looked at the largest, to answer Larissa's question in a roundabout way, round about 1,000 qubits have been assembled using a couple of those different approaches. So you've got a couple of these contenders that are in this foot race to produce a useful quantum machine that so far have about 1,000 physical qubits that they have gotten operating on a processor. And to date, none of those arrays can outperform NVIDIA hardware or any kind of conventional chip that's powering a laptop. So they haven't yet crossed that point where they can do something more efficiently than a classical chip. And so the next question might be, well, how large of a processor do we need before there might be some crossover? And I'll let Larissa assign that question to someone else.
Great. So, Sam, go ahead. Jump in.
Can I rant for one?
Sure, go for it.
On the soapbox. Yes.
Yes, please.
I mean, first of all, I agree with everything Matt said. I think maybe the most important thing to know when you read popular articles about quantum computing is that number of qubits is important, but talking in terms of that is misleading because it's far from the most important thing. So the hardest part about building a quantum computer is not adding more qubits. The hardest part is controlling those qubits without disturbing their fragile quantum nature and being able to operate them for many clock cycles as you would in a computer. And that's what holds back every quantum processor today. For the processors that have hundreds of qubits, it's usually not possible to even do an algorithm that uses all of them because it's consumed by noise before you can do that. And so there are a lot of challenges to getting to useful quantum computing. Scaling up, increasing the number of qubits is one of them. But that's like just talking about a computer by how much memory it has. And the hardest challenge is actually operating it with high fidelity and low error and controlling the quantum mechanics. You need to do that.
Yeah. Maybe I can piggyback off of
sure,
that
go ahead.
answer and then answer the second question. So, I would say error is a huge factor, right? And when we have classical computers, we tell them to do, flip the bit or whatever. We're almost entirely sure that it's going to do that. And we do have some error correction schemes with classical computing. But on a quantum computer, because it's so difficult to keep the quantum state intact, our fidelities are on the order of 99.9, which sounds pretty good, but the errors compound if you have, a circuit or an algorithm that kind of extends. So basically, to get around this, lots of clever people came up with error correction schemes. And so there's this idea of fault-tolerant quantum computing, which is using these error correction schemes, basically grouping together a bunch of qubits to make what's called a logical qubit, so you can account for those errors. And this is great, and this kind of saves us from the fact that there's this inherent noise that we're not ever going to be able to completely get rid of. But these schemes require tremendous overheads in the number of physical qubits. So asking about how many qubits we're actually going to need for certain problems, it might only be 100 or 1,000 logical qubits, but as it stands, resource estimates are now in the millions of physical qubits. And so, how do we get from, what we have today, which is 1,000 noisy qubits, to, millions or tens of millions of qubits if we want to simulate like a tiny molecule that I can do on one of, Sam's cards really fast. It's a long way away.
And when do you think we'll get there? What would you predict? When are we going to see a quantum advantage?
I think it's at least 10 years out.
Sam, what do you think?
I don't know if there's going to be a big bang moment. I think 10 years is kind of as good a guess as I can think of, but there may be. So there's already a very contrived problem that's not useful at all, where a quantum computer can do something and no other computer can. And so,
this is Google's supremacy experiment from 2019.
And a couple others.
Yeah.
A couple others since then. But for a quantum computer to have an impact on a problem related to drug discovery or some of the applications we're most excited about, I at least 10 years is reasonable.
And same for Shor's algorithm,
Yeah.
for RSA encryption. It's kind of the same level of complexity of simulating chemistry as breaking encryption. So, if you had a quantum computer that was good enough to break our encryption schemes, it could also do something useful for chemistry.
Got it. What do you think, Matt?
I'm slightly more optimistic.
Good.
So what we do, we consider NVIDIA hardware, and I'm not saying NVIDIA to plug NVIDIA. They don't need the plug. But for simulating physical systems, you want a processor that can do matrix multiplication, and that's what NVIDIA hardware does. So when we jam these molecules and simulate them using our software running on NVIDIA hardware, what actually happens on an NVIDIA card or a chip, you have a processor, and then you have RAM, you have storage. And so what we try to do is stress NVIDIA hardware to see when will it break, like how big of a molecule can I jam in there before it really chokes NVIDIA hardware. And it turns out what you actually have a constraint on is not processing speed and power, like that holds up. It's storage, it's RAM. So that for us is the first indication, okay, this is the place in a workflow where quantum processing could help. And the reason for that is on a QPU, a quantum processing unit, these qubits don't need to shuttle data off to RAM because these devices, these qubits, these quantum transistors, they remember all that information in their brain. It's oversimplified, it's not technically rigorous, but that's kind of what happens. So you don't need RAM. And so what we do is kind of test to see, okay, given that, how large of a QPU do we need before we could say, at the point where we can say, look, it's going to actually boost the performance. And the resource estimates we do come out at somewhere, what Grace said, somewhere between 100 and 1,000 very high quality qubits. The thing that tantalizes us is we may be able to get away with not needing fully error corrected qubits. So in other words, switches that are as accurate as you have on your iPhone. But there's this intermediate quality. They're not these really crappy qubits, but they're at least error mitigated or algorithmic qubits. And if someone can produce a couple hundred of those on a chip, that could happen well inside of 10 years. And that's what kind of gives us hope, hey, that could be the chip that we could use and integrate into a GPU workflow. So I'm optimistic that with 60 horses in the race, one or more of them may be able to produce that kind of a machine within 10 years. If not, yeah, I think we're stuck with kind of watching on the sidelines for a decade.
Yeah, actually, I'd like to kind of agree with the optimistic tone, maybe more than my initial answer.
Okay.
I think the error bar here is huge, and we're in kind of a pre-breakthrough era, and the nature of breakthroughs is it's hard to predict them, and that could be in hardware, it could be in kind of algorithms or how to make like a clever way to make use of imperfect qubits. But yeah, something earlier is possible. It's a big error bar, especially with so many great groups working on it now.
Got it. Okay. All right. So this is a question we're not prepared on. So just as a warning, but it came to me because sitting here, we're right next to Slack, right? So we have all these quantum stuff happening like beneath us as the linear accelerators out that way, right? And then yesterday I drove down to Analog Devices and I got to drive down the highway and you pass semiconductor company after semiconductor company, right? So here in Silicon Valley was where semiconductors were built and the computing industry was built. Where is the quantum industry going to be built? Do you think it'll also be built in Silicon Valley, leveraging off of that technology? Is it going to be in Europe? Is it going to be in where I'm from in Boston? Fingers crossed. Where do you think it's going to be? Grace.
Oh, I don't know if I'm qualified to answer that. But I think that at least thinking about kind of superconducting qubits or maybe some of the other modalities, we can take lessons from the fabrication of, semiconductors in the valley here. So I would say in those modalities, potentially here, right?
Yeah. Sam?
Yeah, it's a tough question. I think certainly what we're seeing is an emphasis around the world from different countries on trying to make sure it happens there. or trying to make sure at least a big part of it happens in their country. So this is happening with AI as well, and the idea of sovereign AI. But there are dozens of national quantum initiatives now, where in not only America, but many European countries and Asian countries are investing in quantum technology and investing in developing a workforce. And so I'm not sure there's going to be one Silicon Valley for quantum. I think it seems like it's going in a pretty worldwide distributed direction.
Yeah.
Interesting. Matt, what do you think?
I agree with Sam. If you look at the supply chain for the types of quantum computers that are getting built now, it's completely global, and it's and some of the types of components you need rely on things you're not where the envelope hasn't been pushed classically, like lasers, resonators. There's all kinds of components that feed into a quantum computer that haven't been incubated here locally in Silicon Valley. But I think one thing about the center of gravity in Silicon Valley is it does seem like this is a place where big systems always get integrated. Like, AI could have been incubated. OpenAI happens to kind of be here. It's sort of at a system level. It seems like a lot of things keep coming back to Silicon Valley. If you look in the United States right now and say, okay, where's their critical mass of systems development? It's Yorktown Heights in New York, which is where IBM is. I mean, they don't have all their fabs there, but that's kind of big. Amazon is down at Caltech. Google's in Santa Barbara. Both Microsoft's up in Seattle, although they're scattered. The research is all scattered. So it is very, very distributed right now, yeah.
Got it, okay. All right, so I think we have time for one more question. So I think this one, you can choose which way you want to answer it. So the question is going to be, what do you think are the biggest risks and or benefits of quantum computing that we're going to see in the next 5 to 10 years?
Me first?
Sure.
Okay.
Yeah.
Yeah, I think I would just echo what I said before, which is, the biggest risk is breaking encryption, right? To keep our data safe, we need to move to new encryption standards. In the event that a quantum computer, like Sam said, steal now, decrypt later. If your data is important for, the next whatever lifetime of your clients or whatever, you need to move over to those new standards. But then, as I said, if you have a quantum computer that can break RSA, it can do something very meaningful for quantum chemistry, so for healthcare, for materials science. So I think that the upsides are truly tremendous if we can design at the quantum scale like we design at the classical scale. It's a completely new
and do you think that the risk of breaking RSA, is that something that we're worried that a foreign country would be designing a quantum computer that would break RSA or destroy our... Sam's smiling. So
they most certainly are.
Yeah.
Yeah. Okay.
They're spending money on it.
Yeah.
Certainly. Yeah.
Got it. So we just have to beat them. All right, Sam. What are your thoughts? What's the biggest risk or benefit of quantum?
Yeah. Well, Grace is probably right and still a scientist, but I'm no longer a scientist, so I'll give a more hand wavy answer. I think when you have a new type of physics and you figure out how to really control and harness and make use of that, I think you're likely to be positively surprised by things that come out of it that are really hard to kind of draw a straight line from what's known about it when you started. So that's certainly true with electricity and magnetism. Quantum mechanics, the reason I became a physicist is how counterintuitive and interesting and exciting quantum mechanics is, and so I can't help but feel like there's some not intuitive, but very very exciting application of really deeply understanding how to make use of quantum mechanics and becoming experts in that. And I think that's that could be feasible in 10 years.
All right, Matt, close us out. What's your thoughts?
Time's up. I think
You don't get off that easy.
I thought, I suppose this new powerful technology, this emerging technology, like any other new emerging technology in the past, could be used for, quote, good purposes or, quote, bad purposes. It's got that that power seems to find its way into both camps. So I guess the risk is that this new technology could be something that could be detrimental to our national security or detrimental to public safety or whatever it might be. But hopefully that will be massively outweighed by all the good things that can come out of this new compute technology.
Great. All right. Well, thank you. Thanks so much.